get online with other regions.
Okay. So like more quantum computation side, or
Kind of, yeah, not only quantum, AI.
Soon is Akash still there?
Yes.
He's still there. Is working on the caloritronics project, or?
No, he's working on two projects. One project. And the other one is
Yeah. So basically, everybody's still there.
no,
Who's
still left, right?
So
But
I
it's
thought he's doing like half.
no, it's only final finish.
Oh,
And his mission is not
So like in terms of like leadership or is everybody in your project and
No, no, no.
I can later. I have so many questions because last time I saw you was probably 5 years ago.
You didn't change at all.
That's right. We're at the change. I am at least at the age I don't grow anymore.
At some point, you
Just
will
getting
nobody
great.
wants to because that's better than say you're too smart.
It works. We'll normally start about 5 minutes late. I'll let you know the way it works and go from now on. Roll.
She gave her, I got a PhD in Solis University.
Virgin. Oh, I see. I'm this close, like really. If there's world war, you'll be the last place. Oh, let me tell you first. What we do is just stream these live, so
Yeah.
no problem. And the other thing is, if you don't want that channel, you then put it on YouTube. Don't tell them. If you have secrets in
Yeah, give me your niche one.
Okay, well, let's get going. I'm glad to get started with the spring semester version of the Quantum Materials Devices seminar. We have an exciting group of speakers lined up for you to hear, and that posted on the website. It's like all this. The first is See-Hun from IBM Almaden, who will be telling us about Chiral spintronic materials. He comes from Seoul National University. Originally, actually, was a classmate with him, so they know all about each other from the old days. And then he went to Berkeley and Lawrence Berkeley Laboratory for but here you go.
Okay, thank you very much. Very nice introduction, and it's my great pleasure and honor to be here in Harvard. I really appreciate the Philip Kim of providing me this valuable opportunity to give a presentation about the emerging field Chiral Spintronics today. Although Philip Kim couldn't make it this seminar, he promised me that he will watch the recorded video later. So the before starting my talk, let me briefly introduce IBM Research. So IBM Research has 12 institutes all around the world to have the best minds and ideas. And now more than 3,000 the researchers working on AI, quantum, blockchain, cloud, and systems. I'm working in here at the Almaden lab. And as you must be familiar, the IBM has had 5 Nobel laureates about the invention of the STM and discovery of the high temperature superconductivity from the cuprates. And most recently, in Almaden lab has Nobel laureate for the invention of the super high resolution fluorescence microscope. So this slide shows the outline of my talk. So I will talk about the chirality in nature, for example, chiral object, chiral molecules and chiral magnetic domain walls and the interaction with the moving spins. Then I will, basically today I will mostly focus on the current driven motion of chiral domain walls from the various magnetic nanostructures like single layer, perpendicular magnetized layer interface with the heavy metal layers and the synthetic ferromagnet, antiferromagnet, and ferrimagnet system. And then the geometric twist of this current driven motion of chiral domain walls. And then later in my talk, I will spend quite a bit of time to discuss about novel emerging kind of dynamic phase, chiral exchange rate, and anomaly phase in the weakly coupled synthetic antiferromagnetic systems. And then I will conclude my talk. And the chiral molecule, chiral the object cannot be superimposed each other after the mirror image symmetry operations like the left and right hands. And the numerous examples can be found in the nature. And the archetypal example is chiral molecules in the stereoisomers. Stereoisomers means 3-dimensional isomers. And another example is the chiral magnetic domain walls. Usually it's the chirality is set up by the Jaramsky-Moret interaction, which attracts a lot of attention these days from the magnetic and spintronic communities. And the next excellent question is whether spins are chiral or not. The answer is yes and no, depending on the spins are static or on the move. When the spins are static, spins are not chiral because there's no kind of spin spatial dependence, although they are sort of angular momentum. But the spins are on the move, they become chiral because the symmetry is broken depending on the relative orientation of the spin direction and the momentum direction. So the moving spins behave like the screws, and screws, the thread orientation corresponds to chirality. So basically, the moving spins become chiral. It can interact with chiral structures, which means that when the spins are traveling through the chiral structures, then spins become polarized or filtered, or spin's angular momentum can be transferred to the chiral structures. So thus allowing us to do this chiral spintronics. So the people try to observe this kind of large spin filtering effect by injecting the unpolarized spins onto the chiral molecules, but observed spin filtering is much smaller than theoretical predictions, while some other people find the large anisotropy of the emitted photon from the chiral molecules by shining the light and due to the photoluminescence in the presence of the magnetic field. And later, early 2010s, the Israeli group, this group observed very large spin filtering effect by injecting the unpolarized spins into the chiral DNA molecules. And what they found was that the spin filtering is proportional to the DNA wire length. And the same group even observed that the magnetic moment can be switched by applying the chiral molecules and shining the circular polarized light. And most likely, the circular polarized light generates the spin current and spin transfer torque, and that switch the spin, the magnetic substrate. And actually the chiral molecules is sort of enantiomer. Enantiomer is probably you may not be very familiar. Enantiomer is basically isomer. It has same chemical formula, but the structure is slightly different. They are mirror symmetry. And L isomer and D and L and D isomers correspond to left-handed and right-handed chiral molecules. And it is the enantiomer, so the chiral molecule, chirality is very important in the biochemistry and the pharmaceutical industry. Because this chirality is important, is importance of chirality is exemplified this kind of, for example, the thalidomide enantiomer. The thalidomide has a very famous and tragic history. And for example, the left-handed this thalidomide enantiomer can be very effective for the suppress the morning sickness for the pregnant woman. But the other one can be toxic and causes a birth defect. The other, the chirality one. And so the tens of thousands, the cases were reported in the in European country in mid-1950s. And then this company, the manufacturing company, tried to sell and export this medicine into the United States. And this lady in the FDA insistently refused to approve this medicine in the United States. And she saved a lot of cases of this birth defect in the United States. And she won the civil award from John F. Kennedy for this credit. Okay. So basically, the chirality separation and isolation of a specific chiral molecule is very, very important, especially in the pharmaceutical industries. And but unfortunately, the thalidomide is not very effective because thalidomide is in the human body. They interconvert. So it's isolation of the specific the left-handed enantiomer is not very effective. But anyhow, the most cases, the isolation, separation of a specific chiral molecule is very important. And the same Israeli group, actually I grew the film for this magnetic layer, is very interestingly when they spread the 50-50 kind of mixture of the two chiral molecules and spread on the magnetic substrate, perpendicularly magnetized. And then what they found is very interestingly, sticking rate, adhesion rate on this magnetic substrate is highly dependent on the chiral molecule and the magnetic moment orientation. So for example, the left-handed one is more stick to this up-polarized magnetic moment, and the right-handed one is more stick to the down-polarized one. And of course, the non-magnetic control sample shows a 50-50 kind of sticking rate. Okay. So this is very interesting, and this can kind of guide us to find some more effective way to separate the specific chiral molecule. Okay. And this was so very interesting, and it's highlighted by the physics today about 1.5 years ago. And this series of work is basically open the new area of the kind of spintronics based on the chiral molecules. So let me change my gear and then move on to the next, another interesting the chiral object, chiral magnetic domain walls. So let me briefly introduce, can explain what magnetic domains and domain walls are. So magnetic domains are kind of small magnet with a kind of uniformly magnetized. And then although we have a kind of neighboring grains, they're together, they are kind of agglomerate, they are put together, but they are, as far as they are uniformly magnetized, then they all belong to the one domain. But when two neighboring domains are magnetized along in opposite direction, then we say that we have two domains and one boundary. Basically, two domains have a boundary. And this boundary corresponds to the magnetic domain walls. And this magnetic domain wall width is always finite. It cannot be super accurate and abrupt. And this width is determined by the computation of two key energies. So the magnetic domain and domain walls are, this can be described by the two key parameters, the polar angle theta and the azimuthal angle psi in the polar coordinate. And when the system is, magnetic system is perpendicular polarized, there is a theta 0 correspond to up, and theta pi correspond to the down. And of course, theta pi over 2 correspond to the domain wall, because it's in the, exactly in the in plane. And then we have another parameter theta, and the psi. Psi is the azimuthal angle, and depending on this, the psi angle, the domain wall can be classified into two: nil type wall, the other is block wall. Nil type wall is basically domain wall magnetization out of the plane, out of the wall plane. In plane case is a block wall. And then how the domain wall is actually created, right? Then the answer is that basically there are two key energies that are associated with the formation of domain walls. The first one is exchange energy. Exchange energy is kind of favors all magnetic moments along the same direction, so uniformly. They don't like that there's any kind of tilting between them. But once you are aligned, then any direction is okay. But then specific orientation is set up by the second energy, is so-called anisotropy energy. This anisotropy is set up that the all magnetization in the specific axis, kind of z-axis. So here, in this case, z-axis is g-axis. So now, for the simplicity, if you assume that the psi, the azimuthal angle is all uniform, and then the total energy can be described by a very simple form. And then if you apply the variational method, variational functional method, and the Langevin equation, then we have this domain wall profile equation, very simple equation. And this simple equation turned out to be the Sine-Gordon equation. This Sine-Gordon equation is used in the field theory in the high energy physics a lot. And this Sine-Gordon equation has a very simple, non-trivial solution. So 0 and pi. Right? 0 means up, everything is up, one domain, and pi, 0, the other is down domain. And these two states are degenerate, same energy state. So basically, this corresponds to the single domain ground state. But the Sine-Gordon equation is known to have a non-trivial solution. A non-trivial solution is this. And this non-trivial solution is topological Storyton equation. And this has basically one domain excitation. I have two states. These two states are basically degenerate. Okay. Then how does this domain wall profile look like? It's a kind of this case 1, and the other state is up 0, theta 0 and pi, theta pi and 0. Two energies exactly degenerate the same state, but their state is different. Then let's assume that we have a infinitely large domains, kind of magnetic structure. There's single domain, and if we create one domain, then we have an energy differences. This is excitation energy. And then, but we have excitation energy, then can this excited energy can decay into the ground state energy? It's impossible, because how can you get rid of this? Because it's topologically different. It's topologically non-trivial compared to the ground state. That's why this domain wall can be used as a kind of energy data storage. So the information can be encoded by this domain wall and domains. So that's why many people in IBM is interested in the domain wall and domains to use this information, into kind of to store the information effectively. So the people, just in case people in this room may not be very familiar with the spin and the magnetic moment and torques, that I prepared this movie clip from the YouTube.
I am here at the University of Sydney, where the mechanical engineering shop has built this incredible piece of apparatus for me. It is a 40-pound, that is 19-kilogram flywheel on the end of a meter-long shaft. Can you imagine trying to hold this out horizontally with just one hand at this end? It is virtually to a few thousand RPM. And then I'm going to attempt just that, hold it from one end and have it out horizontally. Five, four, three, two, one. I'm going to let go with my left hand. What you'll see is that the shaft remains horizontal. See it go.
Oh. So what, can you see what happened? It have some, I kind of, unfortunately, my time is limited. I have to chop it up. Sorry about that. But you can see the essence of what I'm trying to say. And basically, the fast rotating disk generates the angular momentum horizontal bar direction, like this. And we have definitely the gravitational field pointing down to the ground. And this gravitational field apply the torque and process this angular momentum around this field. This is sort of field-driven torque. Okay? And the main kind of message I'm trying to deliver is that the angular moment, the spin and the magnetic moment is sort of angular momentum. So please remember that spin and magnetic moment is sort of angular momentum. Okay? So basically, torques that change the magnetic moment are classified into two: field-driven torque and the spin transfer torque. And even the spin transfer torque can be subdivided into the damping-like spin transfer torque and the field-like spin transfer torque. Okay? And here, the field-driven torque and the field-like spin transfer torque case, this magnetic moment presses around the torque source, while this damping-like spin transfer torque case, magnetic moments rotate toward this torque source. Okay? And this primary torque, of course, entails the secondary torque, so-called the damping torque. The damping torque is always perpendicular to the primary torque direction. And this damping torque is scaled down compared to the primary torque with the coefficient of this alpha. So alpha is the Gilbert damping. So Gilbert damping is smaller than 1. That's why the secondary torque cannot be larger than primary torque, right? So basically, this is how it works. And note that only the damping-like spin transfer case total angular momentum is conserved, and the other torques are not. Okay? And here, if you add up all these torques, and then we can have one equation. This equation is this kind of renowned equation, this Landau-Lifft-Gilbert equation. And to increase the torque to move the domain wall faster, or the switcher magnetization of the magnetic element very efficiently, we have to increase the torque source or make the magnetization orthogonal to the torque source. Okay, if you do this, then you can increase the domain velocities, or you can switch it best to the magnetic element. And then to understand now the spin transfer torque, we have to understand how actually the spin current is generated in the magnetic metal. We have a magnetic metal here, and this magnetic metal is magnetized along this direction, and we inject the unpolarized spins here. Then these spins are scattered by the magnetic moment on inside the ferromagnetic metal. And then this scattering cross-section is highly depends on the relative orientation of spin and the magnetic moment direction. And then they are parallel. They are more transparent. The other directions are more scattered. Cross-section is larger. Then you know that in condensed matter physics, the electrical resistance is determined by the backscattering, right? The most scattering happens in the other orientation. So that's why outcoming electrons are basically spin polarized along the magnetization direction. Okay, this is so-called repolarization process. And then the spin current is then bumped into the non-uniform magnetic structure like the domain wall. Then due to the total angular momentum conservation, the spin angular momentum is transferred to the magnetic moment, or magnetic moment's angular momentum is transferred to the spin. So consequently, domain moves along the electron flow direction, or opposite to the current flow direction. That's why this kind of spin transfer torque is always move the domain along the electron flow direction, because the majority carrier in metal should be the electron. Okay? Then Then how different is the spin transfer torque from the field-driven torque? So they have now the domain wall. We have 3 domain walls, 3 domains separated by 2 domains, and we apply magnetic field. And then to minimize the Zeeman energy, this or the up-down domain wall should be moved from the left to the right, while the down-up case is moved from left to the right.
In the previous slide, you showed the animation.
Yes.
You can go back.
Okay.
So there is like an H-bar, right, missing, no? Like, I mean, the spin was spin up and then it became spin down, and the H-bar got absorbed the well.
Yeah. Good question. So basically, these are the sort of the repolarization process. Kind of, this spin transfer torque is highly reciprocal process. The angular momentum of the spin or magnetic moment, they are kind of exchange under the total angular momentum conserved. So basically, you can see that this domain wall, it's this domain wall, the spin is actually magnetized along the same direction, right? I didn't actually go into the very detail about how the domain wall kind of the spins are kind of repolarized, but basically this has some kind of information how they are basically repolarized. Okay, so here that's why the domain wall velocity kind of sign is opposite to each other, and the wall-to-wall distance decreases. Okay, on the other hand, the spin transfer torque case, independent of the domain configuration. If you apply the current from the right to the left, then domain wall moves along the same direction. And the wall-to-wall distance are basically conserved. And then now, as I mentioned earlier, this domain wall and the domains kind of encode all the information in the kind of any storage devices or logic devices. And then if this happens, then 3 domain will become just 1 domain, then the data is lost. But this case data is preserved. So this is basically the most important kind of mechanism that how the spin transfer works, and it can be used in the useful kind of storage devices. And then the problem with the SCT-driven torque is the magnetic
bubbles where you have a up bubble and a down with circular.
Right. So kind of this case is about hundreds of nanometer for the in-plane case, but the out-of-plane case, you can go down to tens of nanometer.
But what is the domain wall flat and straight like that? Or?
Domain wall, you can, domain wall width is very small. It can be a kind of tens of, kind of below than 10 nanometer.
Yeah. Okay, but what is it? Straight line?
Oh, this is compared to this is different from the bubble domain wall.
Yeah.
Right. Bubble domain is kind of sort of media, but this is a kind of one kind of wire. We have just 1 domain, and we create the mid virtual domain walls. It's kind of is sort of different from the bubble domain wall.
So we used to think about a long wire.
Right, exactly. So I will show you later how that actually measure the locate the wire, kind of the domain wall and domains with a kind of microscope. Okay? So the conventional STT case, the maximum domain velocity is kind of limited by many factors, and all kind of 100 or 200 meters per sec, and this which limits actually the access time of the actually devices. Then we cannot improve the switching speed and the device speed. So how can you improve further than that? Basically, how can you develop the even high kind of faster device and based on the faster domain wall? And previously our group and the MIT group and Jeffrey Rich group showed reported very high velocity, domain velocity, based on a completely new type of torque. We so-called this spin-orbit torque. And spin-orbit torque is basically the combination of the two torque. One is the field-driven torque, and the other is the spin transfer torque. And this field torque is coming from the kind of internal field generated by the Gyro-Moria interaction. The Gyro-Moria interaction is basically set up, you know that it probably might be very familiar, set up the specific chirality due to some anti-symmetric nature. You can see that if you switch M1 and M2, then they change the sign. And this DMI is induced in from the broken inversion symmetry, like interface or in the bulk case non-central symmetric system. And as you can see here, this Hamiltonian is exactly Zuda's color. So if you invert it, then the sign changes. Okay. So if you invert it, then always the sign changes, which means that this DMI sign changes. And the interfacial DMI case it favors Needle. So you remember what Needle is. Needle is basically magnetization is out of plane, out of the wall plane. Okay. And one of the kind of key ingredients, this slide shows how this spin-hole torque works. We have which is one of the key ingredients of the spin-orbit torque. And when you apply the current into the non-magnetic heavy metal layer, and then the unpolarized spins are injected here, then they are scattered by the non-magnetic impurity, and which are deviated by by the scattering of the non-magnetic impurity, and then which make the spin current out of plane due to the relativistic spin-off interaction. And then these spins are accumulated at the surface, and when you place this ferrometal layer on top, then this magnetic moment is filled the damping spin transfer torque and rotate the magnetization toward this spin direction. This is so-called the spin-orbit torque, spin-hole torque. And then we have the magnet structure is because this magnet structure has broken inversion symmetry, and the spin-orbit interaction is large, so the Gyro-Moria interaction is innately involved. And as I mentioned earlier, DMI set up the specific chirality and favors the needle, and that's why the up, down, down, up, their magnetization direction is like this, because chirality is conserved. And then to set up this chirality, so chiral nature of the domain one, the DMI internal kind of local DMI field is applied, is generated along this needle direction. And then when you apply the current, then the magnetization is used to be like that, and it rotate this way, because due to the damping speed transfer torque. And then we have a DMI field and the magnetization like that. They have a finite angle, and this field applied the magnetization, the field-driven torque. Magnetization rotate out of plane like this. And this magnetization rotate out of plane. That's why the domain will move. And their motion directions are exactly opposite to each other due to the chiral nature. And the domain wall moves along the current flow direction independent of the domain wall configuration. Okay? And this is opposite direction to the conventional spin transfer torque. As I mentioned to you, conventional spin transfer torque, domain wall moves along the electron flow direction, but this is current flow direction. So this is entirely new torque and much more powerful and tunable and versatile. And then this slide shows how we measure. You can see that we have the wire geometry is like that. And however, the stack information is like this. And platinum, cobalt, nickel, mercury on top. Here the platinum is the spin hole torque source, and the interface of the platinum and cobalt here is induced Gyro-Moria interaction. And then now we have here we use the microscope, curve microscope. Curve microscope is combined technique between the microscope and the magno-optical curve effect. And then here is the dark and the bright area correspond to the into and out of the magnetization direction. of the screen. And then when you apply the current pulse, and then you can see the domain wall moves along the current flow direction, and the independent of this domain wall configuration like that. Okay. And then how we measure the domain velocity? We take the shot, image shot before applying the pulse, and then apply the pulse. We also take a shot, and then we can measure the displacement of the domain wall, and then this displacement of the domain wall divided by the current pulse, then we can have a domain wall velocity. And we vary the underlayer, the spinor torque source, platinum, iridium, palladium case. It shows that the domain wall moves along the current flow direction, while the gold case is opposite. So this shows that the domain wall is driven by the spin orbit torque for the platinum, iridium, palladium, while the gold case is conventional speed transfer torque. Okay. Although the platinum case is maximum. And then this chiral domain wall motion by the current is more more dramatically and pronounced by this experiment. Why I applied this in-plane field, and the in-plane field is collinear direction into the along the local DMI field, and then field direction is the same direction, and which added up for the field torque. That's why the domain velocity increases, and when you change the sign and start to compensate the DMI field, then the domain velocity decreases, and completely compensate, the domain will start moving. When you increase further than that, then the domain moves in the opposite direction because the chirality changes. And then due to the chiral nature of the domain walls, up, down, down, up, their internal field is opposite to each other. So the velocity versus this hx field curve is actually mirror symmetric with respect to the y-axis. And this, you can see that the slope sign is opposite, and the crossing field sign is also opposite. And this slope is proportional to the domain width and the spin orbit torque, spin hole torque. Okay. On the other hand, when you apply the orthogonal field, the field is orthogonal to transverse field is orthogonal to the local DMI field, then velocity versus HY field is exactly identical for the up, down, down, because it's orthogonal due to the orthogonality. It doesn't affect the chirality at all. Okay. And actually our device, the wire is finite width, and then so finite width, we have a up, down, down, up, and this DMI field stabilize the Neal wall. You can see the field direction is opposite to each other. And then when you apply, and this DMI field is always happy, only happy when the magnetization is in the Neal type case. It's completely when the magnetization is perpendicular to the wall direction. Then DMI is always happy. If it's away from that, then DMI start to be unhappy. But when you apply the current, and the spin orbit torque rotate the magnetization this way, then it's not DMI at all, the Neal wall at all. Then DMI start to be unhappy. To decrease the DMI energy, the domain wall should be tilted like this way. And tilting angle sign is opposite to each other because this field direction is opposite to each other. But the problem is that then if you rotate, then it's kind of rotate like this way. It's vertical, it's kind of completely horizontal. But this is not favored by the domain wall energy because remember that the domain wall energy is excitation energy of the one domain wall from the one single domain. And it costs the energy. If the length is large, then it costs a lot of energy. So that's why the domain wall tilting angle is determined by the competition between the DMI energy and the domain wall energy. Okay, then just now have basically symmetry is broken. Symmetry is broken, but the domain velocity is still the same. But this kind of degeneracy can be lifted by injecting this domain, the tilted domain wall, into some geometric twist like this. Have this Y-shaped wire, and here, so basically domain wall is here. This up, down, down, up, their tilting is opposite. basically their response should be different. For example, up-down domain wall is faster, going faster for the upper branch, while the down-up domain wall is move faster for the lower branch. And this asymmetry of domain wall motion increases when you increase this branch, Y-shaped branch. You can see 60 degree, 90 degree, 100 degree. You can see that the asymmetry increases. And then,
what's the side scale? Oh, there's
right. So sorry, I didn't actually put the scale bar. Yeah. And then I'm not going to too detail, but what we see in the underlying mechanism is basically the two relaxation parameter angle, relaxation time. Basically, the domain wall is injected, and then they bump into the new environment. Then domain wall should be relaxed into new environment. And then domain wall magnetization and the domain wall tilting angle should be relaxed in new state. And this relaxation scale, time scale is very different to each other. Domain wall magnetization much faster to relaxed compared to domain wall tilting angle. So if by applying the very short pulse or some pulse, longer pulse, we can kind of maximize the two differences. For example, if you apply the very short pulse and when you inject the two domain walls, up, down, up domain wall, then it's two domain walls kind of bifurcate. They all injected up, upper branch and down, lower branch. But when you apply the very long pulse, then domain wall is only, two domain walls injected on the upper branch. In the lower branch case, they are kind of annihilate each other, destroyed. So kind of forthgoing domain wall is kind of cut up by the follow-up domain wall. Okay? And the vice versa thing happens in the down, up, down domain wall, like this. The short pulses, then they are bifurcate. But the long pulse, so two domain walls kind of injected only the one branch, and the branch, the direction is opposite when the polarity is switched. So if we use this, then we can maybe develop some logic devices. And then this Y-shape concept can be generalized to the curved wire.
How fast do they move? Again, I'm thinking about
They can be about 400 meters per second. 400 meters per second. Yeah, and which is about 2 times or 2 or 3 times large, kind of faster than the conventional spin trapezoidal. Yeah. Okay. And then is more kind of generalized into curved wire. The Y-shaped wire, Y-shaped branch is basically one point kind of twist, right? Basically, just a new environment is happening is only one point. But the curved wire case, every point is continuously changes. Okay, so you can more clearly see what's going on. Okay, this curved wire has characterized by the width of the wire and the radius of wire, and then we have an additional very important parameter is curvature of wire, and curvature has a sign. As basically the domain wall is moving, the domain wall or the current is applying along the clockwise, then we define it positive curvature, and anti-clockwise is negative curvature. Okay, and then what we observe is that now here it's clearly see that these are the movie clip for the straight wire for when you inject the multiple chiral domain walls. There is a wall-to-wall distance or conserved, and this is most important underlying mechanism about this current-driven spin-traps, current-driven chiral domain motion for the application, the technological applications. And then, but when you inject the two domain walls, up down of domain wall for the positive curvature, and then the down up is faster than the up down. Okay, that's why the wall-to-wall distance increases. Okay? But on the other hand, curvature is negative case. The same one is the up, down, up is injected, then it's the domain wall is annihilated because forthcoming domain velocity is slower. It's kind of caught up and so domain wall is destroyed, annihilated. And then if you switch the polarity, down, up, down, then it's basically this happens similar to what happened here. Wall-to-wall distance this decreases, annihilate, and this happens like this. Okay. But this is really bad news and sort of nightmare for the development of devices.
What's eating it up?
Why eat it up?
Yeah.
Oh, because this domain wall velocity is smaller than that. So when you're moving that, they are kind of collapse each other. That's why the domain wall, three domains become just one. Right. Like this. Yeah. That collapsed. Three domains become one domain. Yeah, that's what happens. As I mentioned, this is a really bad news for the kind of technological applications because to increase the density of the device, at some point we have to make this curved wire, right? And we have to like this. But this, when you inject the multiple domain walls, but many information is gone at the curved region. This is a really big problem. Then how can you resolve this problem, right? And we have a good solution. And these few years ago, we discovered this kind of very high domain velocities from the two magnetic layers kind of combined. Kind of two magnetic layers. These are magnetic layers. Two thin magnets are combined, separated by the thin the space layer, the ruthenium layer, and depending on the ruthenium thickness, the exchange coupling is different. This is so-called synthetic antiferromagnet. Basically, they are antiferromagnetic coupled. But the thickness is different of the ruthenium, then it becomes ferromagnetic coupled. We call this a synthetic ferromagnet. And then, very interestingly, if you use this, then the domain velocity is very high. And then also because they are more or less macroscopically non-magnetic, so it is very inert to the external any agitation or the perturbation. That's good. Then why the domain velocity is high? Because we have another exchange field is here. Exchange field can be much larger than DMI field. So we are using some new field for the field-driven torque. And for example, here the exchange field can be described by the Heisenberg-like interaction. And then we have depending on the sign of the exchange constant, they are parallel or antiparallel coupling. And then they are all ground state. And then basically no field is generated. But if you apply this spinor torque, then they may not be the collinear. Then if you have that non-collinear, then we have a restoring field is generated. And this restoring field is called the exchange field. And this exchange field generates the torque. And this torque is correspond to the exchange field torque. But you can see the exchange field torque is exactly always opposite to each other. Okay? Then if you assume that this magnetization is in each sublayer's magnetic, the domain wall magnetization, then this case is up, down is a field kind of synthetic ferromagnetic case. Then this torque is cancel each other. But the synthetic antiferromagnetic case, they're up, down, up. Their field, the torque direction is opposite. They're added up. That's why the domain velocity can be very high. So this exchange coupling torque is nullified in synthetic ferromagnetic case, while the synthetic antiferromagnetic case, they are added up and they boost the domain velocity enormously. And this is what we observed from the experimentally. You can see that the ruthenium layer, depending on ruthenium space layer thickness, you can see that 2 angstrom, 6 angstrom, they are ferromagnetic coupled, and 4 angstrom, 8 angstrom, they are antiferromagnetic coupled. And then we pattern device, measure the domain velocity. You can see that the domain velocity is significantly increased when they are antiferromagnetic coupled. Again, we can see the clear correlation between the net magnetization and exchange coupling constant. sign and the domain velocity. And the more interesting is that even the antiferromagnets coupled case, they are more compensated. You can see that these are the EG-axis loop. They are more compensated, so the remnant magnitude is small. Domain velocity is even higher. Okay, so our model shows that they are completely compensated. Then its domain velocity can be even higher than 1 kilometer per second. And recently, some other groups, this MIT group and some Singapore group, observed that even higher than 5 kilometers per second, and which is very close to the kind of sound wave. Sound wave. So this is very interesting because sound as phonon is known to be related with this damping. Okay, and then it becomes supersonic. If the domain velocity is supersonic, then it can be free of the damping. Then even the domain velocity even can be further than that. It's quite interesting. We have a very interesting regime. And then when you measure the domain velocity as function of the internal field, then it's previously the single layer case is the monotonically changes, but you can see that this is distinction of the synthetic antiferromagnets case. It shows the broad maximum near the zero field. This is distinction. And then this synthetic antiferromagnet domain motion physics can be extended to even the ferromagnetic system, cobalt gadolinium bilayer. Cobalt gadolinium is, you know that when they make a bilayer, then at the interface, their antiferromagnetics coupling is very strong. And the cobalt is transition metal, gadolinium is rare earth metal, and the Curie temperature is very different. The cobalt Curie temperature is much higher than gadolinium, but at zero temperature, cobalt moment is significantly smaller than gadolinium. So at certain temperature, the magnetic moment should be vanishes because they are compensated. Okay, and this is at this temperature, magnetic vanishes while the coercivity is and the magnetic field, the threshold magnetic field above which domain will start to be depinned, diverges like that because it's more or less their macroscopically is non-magnetic. Okay? Because it's inert to the external any agitation or kind of perturbation. But there is a now very important difference between the cobalt and gadolinium. It's basically gyromagnetic ratio is different. Gyromagnetic ratio of the cobalt is about 2. Gadolinium is 2.2. And what gyromagnetic ratio is basically exactly the ratio between the magnetic moment and the angular momentum. And what you learn is very important thing is that the static property of the magnetism is determined by the magnetic moment. But the dynamic property, like a kind of very ultra-fast motion of domain or whatever, is determined by the angular momentum rather than magnetic moment. So basically, this a little bit kind of looks complicated, but the main take-home message is that at the angular momentum compensation point, the domain velocity is maximized. So then what happens in our synthetic antiferromagnetic case, cobalt nickel cobalt, they are same magnetic material. Basically, magnetic compensation point is the same as angular momentum compensation point. Okay. But this case is, you can clearly distinguish between the two cases. Okay. And then now previously the antiferromagnetic case, at the single layer case, when you inject the domain wall into the Y-shaped wire, we can see the very large asymmetry. But what if you the parent device from Y-shaped wire from the synthetic antiferromagnetic case, you can see that the image asymmetries disappeared. Why this happened? Because synthetic antiferromagnetic is up, down, up, they're coupled. And these are up, down, up. They are trying to compensate each other. That's why they're basically symmetry is gone. And then now, what happens in the curved wire case? Okay, curved wire case, you can see there, all-to-all distance is now same. So that while they're two domain wall, up, down, up domain wall, they're traveling in the wire, the curved wire, they are all conserved. So basically, I mentioned to you, I have some big problem with the single domain wall, and it's kind of single layer domain wall of the chiral domain motion. Multiple domains injected, there is a lot of domain information is gone. But if you use this standard antiferromagnet, then these kind of problems can be resolved. Okay. So this is kind of made some large impact. So the maybe this is now, unfortunately, these are the kind of one of the main results. The later maybe, but I'm going to speed it up. Okay, so now go back to the synthetic antiferromagnet. It's a kind of, this is the most recent results I published, and I have some Yonglong here, and I actually when I met him at I think last year in the March meeting, whatever I explained to him, and he seemed to be very interested in these results. And anyhow, have a go to the very weakly coupled exchange coupling regime. Now the ruthenium, 8 angstrom ruthenium, exchange coupling is negative. So the antiferromagnetic coupling. And then you can see now if you see this interface layer thickness, cobalt layer is 1.5, 1.5. Which is significantly thinner than the one monolayer, which means that the cobalt layer doesn't cover the ruthenium layer entirely. Then, so we have some island like this. Then some nickel layer is interfacing ruthenium layer, but the cobalt ruthenium cobalt exchange coupling is much larger than the other interfaces. Cobalt ruthenium nickel or nickel ruthenium nickel. So by tuning this cobalt layer thickness, we can further tune the exchange coupling. Not only this ruthenium layer. Okay, this is a kind of new technique, but the thickness modulation should be very, very accurate. Fortunately, my system can tune even the 0.1 angstrom by tuning this kind of shutter. So basically, this cobalt layer, by tuning this cobalt layer thickness, interfacing the platinum, we can tune the net magnetization, and then we measure this EG axis loop, then you can systematic changes, and then we pattern the device, and then you can see that the domain wall velocity is very large for the more compensated one due to the exchange coupling torque, as I mentioned earlier. And then when you measure the velocity as function of the transverse field, not very remarkable. But when you measure velocity as function of transverse field, you can see that the very kind of dramatic change of the domain velocity. For example, this black curve, only application of 500 Western field collapse the domain velocity from 500 meters per sec to the 0. This is sort of phase transition. To understand what's really going on, we carry out the micromagnetic simulation here. So we change the exchange coupling constant, 0.5, 0.3. So minus means that it's a negative number means the exchange coupling is antiferromagnetic. And then while the other parameters are all fixed or they are all fixed and obtained from the experimentally or previously obtained. And you can see the positive field doesn't change much, but the negative field case, you can see the dramatic changes. Okay? Something is going on. And then to understand what's going on, we carried out this Q means that this position and displacement as a function of the time, kind of time reserved simulation. Okay, when you apply the positive field case, motion is kind of linearly displaced, which means that the Q dot should be the constant. So the domain velocity is constant. So to understand what's going on, we did some time time snapshot, time resolved snapshot here. The lower layer, upper layer is the top view, and the red and blue corresponds to the up and out of and into the screen of the wire, the domain wall, and then domains, and the white arrow means that kind of projected domain wall magnetization from the top. Okay, and you can see that the domain wall magnetization or steady state or the structure is stable. On the other hand, when you apply the negative field, is kind of B correspond to B, then you can see the domain wall position is kind of oscillate. You can see the clear oscillation. And they are locked to each other. And additionally, very interestingly, lower layer case, you can see that domain wall magnetization kind of oscillate, magnetization oscillate. And the upper layer case, the magnetization is kind of precess. Precess means that the chirality actually oscillate. Chirality is right-handed, left-handed, right-handed is oscillate. You can see that, right? And then another thing is that another important thing to note is that this oscillation precession is not stochastic. They are all synchronized. They are very well synchronized. And then when you apply the smaller field, then it's the period is kind of increases or the frequency decreases, and still you can see that the precession and the oscillation happens, and these are still synchronized. Now this simulation is micromagnetic simulation. Micromagnetic simulation is sort of black box. When you input a lot of parameters, tens of parameters, and then you see the results, and you don't see what's really going on inside. Then basically, you cannot have any insight of the physics. So we need some analytical model. So we developed an analytical model, and then what we observe is that you have here two coupled domain wall, and then Can you speed up? Lower, yeah. And then you have like this, and basically the important message is that the total angular momentum is conserved, and the angular momentum of the one angular momentum is transferred to the other one. Okay? So this is a new type of the angular momentum transfer torque, because the two angular, okay? And then this means that, what it means is that when you apply the current into this coupled wire, and the one domain wall should be moved faster because the environment is very different, but they are coupled, then faster domain wall should drag the slower one, but the total angular momentum is conserved. And then this is kind of in this room may be very familiar with Coulomb drag. So I'm not going to go to the very detail of Coulomb drag. But this shows a very similar behavior, because Coulomb drag's underlying physics is that the total linear momentum is conserved, and the active layer's linear momentum is transferred to the passive layer. And this is similar. So basically, fast domain walls angular momentum is transferred to the slow one, because the total angular momentum is conserved, and because the exchange coupling interaction doesn't dissipate the total angular momentum. And then it's basically then the problem is that when this drag is basically drag strength is the domain velocity difference, and this domain velocity is larger than certain value, then the domain wall structure is not stable anymore, because so drag strength, this energy is converted to internal degree of freedom. That's why the domain wall start to be kind of getting messy. This is we call it this is a new phase, is kind of Coulomb exchange drag anomaly. This is unstable domain wall dynamic phase. This is exactly what you observe, and then this is shows that what we observe that when the drag is larger than some threshold number, then domain wall velocity is kind of collapses like this. It doesn't follow the domain velocity kind of this way, because if the velocity is the drag is larger than some threshold number, then domain will start to be kind of this energy difference. The energy difference is converted to internal degree of freedom. Okay. This is a new driving phase. And but the static antiferromagnets case, this drag effect is much smaller than synthetic antiferromagnets case. That's why we didn't observe any this anomaly phase. And then this shows that actually the microwave simulation and the analytic model simulations, when you apply the positive field, as you can see the domain wall is kind of very stable. But when you apply the negative field like this, then it's domain wall. So these are the lower layer, upper layer, and the side view and top view. You can see that the lower layer magnetization is kind of precess and oscillate, but this is oscillate, this precess. And when the precess means that the domain wall chirality is oscillate, like this. And then you can see that the ferromagnetic coupling case, you don't see this FD correspond to the precession frequency. And frequency 0 means that it doesn't, is kind of stable. Only antiferromagnetic phase, we see that this oscillation. And if exchange coupling is too large, then they are locked to each other very strongly, so no phase happens. And then it's now very close to the end. Now if you plot this velocity or frequency, the anomaly phase oscillation frequency as a function of the net magnetization, so MR means the remnant magnetization, 0 means the completely compensated, and when you're away from the completely compensated regime, the precession frequency is linearly increases, and this kind of reminds us of the massive Dirac fermion. And the massive Dirac fermion is kind of, we have a Dirac equation, is kind of governing equation. And when the mass is 0, then the Dirac equation is reduced to the Weil equation. And so when you Weil equation have the chirality is a good quantum number. And so we have two islands, the chirality is well conserved, like what we observed for the strongly coupled case. But when we have a mass have, there is Dirac fermion gets massive, then the chirality is not good quantum number anymore. Then they start to oscillate. Kind of right-handed become left-handed, right-handed, left-handed. And then this frequency is exactly proportional to the mass of M. Okay. So basically, the magnetic moment in the magnetic structure is equivalent to the mass in the classical mechanics or kind of quantum mechanics, whatever. So basically, this is very similar to what you observe. So the chirality oscillation frequency is proportional to the net magnetization. It's very similar to like this. So this is more or less my last slide. So let me summarize my talk. So basically, we have another knob, the chirality, and the chirality is coupled to the spin, and the spin can couple to the charge through the exchange magnetic resistance. So basically, we can control the magnetic resistance and the device using the chirality, kind of indirectly, sort of, or even you can directly. So this is kind of, it has some new opportunity to using the bicycle when when the spins are moving, then you have another attribute or character, chirality. So you can have some new exciting opportunities to develop kind of devices with the new functionalities. Thank you very much for attention.
Time for a couple of questions. I guess I have one is when IBM finally sells this and I buy it in a box, I put a microscope